Hello, I hope you're all doing well. Today I'm going to be covering rational functions, which is a really simple chapter. There's not much going on as well with this one. We just need to understand, I would say limits, but in this case, in this chapter, they're not calling them limits. It's as x approaches. And first we're going to understand the vertical asymptotes. Then we're going to do horizontal asymptotes. Once we're done with that, we're going to be covering slant asymptotes, which is basically a straight line. Now, starting off with the first one, as x approaches a, you can call it negative if you want. As x approaches a from the left side, x is less than a but close to a. So let me give you an example. Actually, we can understand this from this graph. So we have, let's say x is approaching 0, negative. Well, x isn't really 0, right? Like this is x equal to 0. You can tell that the function is approaching x, As the function is approaching x, it's not really reaching x equal to 0, but instead it's 0, negative. Now, coming from the left side, what's 0, negative equal to? Well, we have -1, right? Then we have -0.9, and -0.8, all the way to -0.1. But we need a number less than -0.1 that is closer to 0. So I would try and explain this as -0.00000001, which is not equal to 0, but it's approaching 0 from the left side, if that makes sense. Now, as x approaches a positive, means that x is approaching a, but from the right side, x is greater than a, but by a very small margin, but it's close to a. So let's have a look at this one. As x is approaching 0, but from the right side, that's why we have this positive sign. X would be approximately equal to 0.0000000001. It's not equal to 0, but it's approximately equal to 0. And it's approaching it from the right side. Now, as x approaches infinity, you can tell as x approaches infinity, x increases without bound. So you need to memorize this. As they mention, x increases without bound. That means x is approaching infinity. That's just another keyword. Now, as x approaches negative infinity, x decreases without bound. So x is going to negative infinity. What is f of x equal to? What is the y value? As x approaches negative infinity, y, in this case, equals to 0, right? Is it equal to -1? No. Is it equal to -2? No. It's in fact equal to 0. Same with the right side. As x approaches infinity, we have the y value, which also equals to 0. Well, it's approaching 0. It's not equal to 0. Now, we have f of x. The output approaches infinity. The output increases without bound, as in this case. We have the output, which is approaching infinity. And we also have the y value, which is approaching negative infinity. You can tell negative infinity. As x approaches 0 from the left side, the output approaches negative infinity. The output decreases without bound. Now, f of x approaches a. You don't have any left or right sides in this case. It is approaching simply a. Now, what I want from you is to not memorize this, but just, it comes with practice. If you want to memorize it, go ahead, but you don't really need to. Like a negative is just from the left side, a positive is from the right side. We all know what infinity means. Without bound translates to infinity. increase positive infinity, decrease negative infinity, and yeah, that's pretty much it. Moving on to this, as you can tell, we have, as x approaches 0 from the left side, there we go, 0 from the left side, we have f of x, which tends to negative infinity, and as x approaches 0 from the right side, f of x tends to infinity. Now, what about these two? Well, this basically tells us that x is a vertical asymptote. Now, let me just sneeze really quick. Okay. Let me teach you this trick before we move on. If I have f of x, let's say, and it equals to x plus 2 multiplied by x plus 3 divided by x minus 1. You take whatever is in the denominator of this rational function. I'm sorry about this. I didn't tell you what a rational function is. A rational function is basically a function as a fraction. So it's basically two polynomial functions divided by each other. So f of x, let's say, equals to h of x divided by g of x. And what is a polynomial function? Well, it's simply a function with a degree that's a positive integer, right? So I have x plus 2 in this case, divided by x plus 3. We've taken polynomial functions. I believe there's a video on this. Anyways, it's divided by x minus 1. Now, this is a rational function. It's just a fraction where you have two polynomials divided by each other, polynomial functions. Now, how do I find the vertical asymptotes? What's a vertical asymptote? It's basically an x value. So in this case, the x value equals to 0. And you have infinities at this certain x value. It doesn't necessarily mean that we have negative and positive infinity. It could actually look like this. Let me just give you an example. Let's erase this. The function could actually be approaching infinity from both sides of x. Doesn't always have to be negative, positive. But let me show you what I mean by a vertical asymptote when you don't have a graph. Let's say you're just given this function and you're asked to find the vertical asymptote. So what do? You simply take the denominator, which is x minus 1, and you place it equal to 0. Then we simply have x equal to 1, and that's your vertical asymptote. It's that simple. But the question is, how do I solve this? How do I find whether the output approaches negative infinity or positive infinity? Well, you simply plug it in. If I have f of x equal to x plus 2 multiplied by x plus 3 divided by x minus 1, the first step you can do is, as x approaches to 1 minus, which is from the left side, you can plug this in. You're going to get, pull out a calculator and simply plug in, what is 1 minus? Well, it's simply 0.99999999, right? Plus 2 multiplied by this number plus 3 divided by, you plug in this number as well, and then you subtract 1, you're supposedly going to get a really huge negative number, which basically means that it's decreasing without bound, which is negative infinity. You do the same with 1 positive, which is simply 1.000001 minus 1. Then you're going to simply get a positive infinity. And that is if you want to graph it, or if they're asking you what is the output when x approaches 1, let's say, from the left side, or when x approaches 1 from the right side, and you can't use a calculator on that specific question. But if you can use a calculator, you can just graph it on decimals, you can tell what the answer is. Moving on. A vertical asymptote of a graph is a vertical line x equal to a, x equals to 0, where the graph tends toward positive or negative infinity. I told you, it doesn't have to always be positive and doesn't always have to be negative. It could be both, it could be one of them, it doesn't matter. As the input approaches a from either the left or the right side, we write as x approaches a from the left side, f of x could be positive or negative, or as x approaches a from the right side, f of x could be positive or negative. Let's have a look at the horizontal asymptote. A horizontal asymptote of a graph is a horizontal line y equal to b, where the graph approaches the line as the inputs increase or decrease without bound. We write as x approaches infinity, or as x approaches negative infinity, f of x tends to b. Now let me teach you this trick with the horizontal asymptote. Let's say f of x equals to, remember, with horizontal asymptotes, we're always approaching infinity. So x approaches infinity, and f of x, let's write that down, x approaches negative infinity. With both infinity and negative infinity, you should get the same exact answer, which is b, which would represent your horizontal asymptote. Now let me give you an example where you get 0. Let's say f of x equals to x cubed plus 2x squared plus 3x divided by, let's say, x squared plus 5x, and x approaches infinity. Now if you've watched the power functions video and I asked you to find, let's say, the output as x approaches infinity for only the green shaded polynomial, which is this one, you would simply take the leading term, which is x cubed, you would plug in infinity, you would get infinity cubed, you would simply get infinity, right? And that is true. But with rational functions, what do? It's a very simple trick. You take the leading term, that's why you need to understand leading terms. You take the leading term of the numerator and you take the leading term of the denominator. So we have x squared and x cubed. It just happened to be that the leading terms were rearranged properly in this case. It may not be the case with every single question, but in this case it just happened to be that x cubed was in front, same with x squared. So now I have x cubed divided by x squared, and remember, okay, just let me actually change this, I messed up. Instead of x cubed, okay, let's erase this. Okay, let's just have x as the denominator. And no, let's keep it as x squared. Let's erase this. I'm sorry, I did this really quick. Okay, let's go with x minus 3. Okay. Now, you take the leading term of the numerator, which is simply x, divided by the leading term of the denominator, which is x squared. And f of x as x approaches infinity. How do I solve this? Now you simplify them. We have 1 divided by x, right? X divided by x squared is simply x divided by x times x. These two cancel out, you have 1 divided by x. Now, as x approaches infinity, I plug this in. What do I get? 1 divided by infinity. And if you have a calculator, just pull out your calculator, and what do I want from you is to simply divide 1 by a million. So let me pull out my calculator. I hope my phone doesn't explode. 1 divided by 1 million is, okay, where should I write it down? Okay, let me just pull out this just so we have some more space. Okay, 1 divided by a million is simply equal to 0.00001. Not sure if that is correct, but you have a lot of zeros going on. And what does that tell us? It tells us as we increase this, as this approaches infinity, this number will simply be equal to 0. So always, always, always remember that 1 divided by infinity or 1 divided by negative infinity, both equal to 0. This is a rule, just memorize it. 1 divided by infinity or 1 divided by negative infinity equals to 0. So in this case, as I find as I find the output as x approaches infinity, I get 0, right? And same with f of x as x approaches negative infinity. For 1 over x, this basically equals to 0 as well. So what does this tell us? It tells us that 0 is in fact a horizontal asymptote. Now let me give you another example where you don't get 0. You get a different number. Let me erase this. Okay, let's say we have... okay, let's go with f of x, which equals to 3x cubed plus 2x squared divided by negative 4x cubed plus 5x as x approaches infinity. What do? We take the leading term in the numerator, which is 3x cubed. We take the leading term in the denominator, which is negative 4x cubed. Dividing these two, I'm getting a negative 3 over 4. Now, as x approaches infinity, well, I can't really plug in infinity, right? There is no x. So what's the answer? It's just negative 3 over 4. And as x approaches negative infinity, for f of x, well, you're just going to get negative 3 over 4 as well, because you can't really plug in negative infinity. So this basically means that negative 3 over 4 is a horizontal asymptote as well. Now, when do we not have a horizontal asymptote? That's the question. When does the horizontal asymptote... Just give me 1 second. Okay, we're good. Okay, let me just... Okay, there we go. I need to drink water. Just 1 second. Okay, I'm back. So what was my question? Yeah, the question is, when do I have a rational function that doesn't have a horizontal asymptote? And that is very simple. Let's say we have 3x cubed as well, minus 2x squared, divided by 5x squared, plus 2, as x tends to infinity. If I take the leading term in this case, I'm getting 3x cubed, divided by 5x squared. If I divide, 3 divided by 5 is just 3/5. X cubed by x squared is x, correct? Now, if I plug in infinity, what do I get for f of x? Well, plugging in infinity, I'm simply left with 3/5 multiplied by infinity, which equals infinity. Do I see any number going on? Do I see a b value? B is a constant, right? They should have wrote that down, but B is a constant. I don't see any constant going on. So I get infinity, and if I plug in negative infinity, I'm getting negative infinity. What does that tell us? It tells us that basically means there is no horizontal asymptote. And when does this happen? It happens when the leading term of the numerator has a degree, as you can tell, 3, greater than the leading term of the denominator. So when you have, remember this, leading term, let's say xa divided by xb. If a is greater than b, that means you do not have a horizontal asymptote. Are we good on this? If a equals to b, that means you do have a horizontal asymptote, And it depends on the coefficients of the numerator and the denominator. Let's say this is 2 and this is 3, and this would simply be 2 over 3, since xa and xb would cancel out. Now, what if b is greater than a? That means you do have a horizontal asymptote, and it's always equal to 0. Why? Because let's say I have x squared divided by x4. Well, this is just 1 over x squared. Plugging in infinity, you're getting 0. Plugging in negative infinity, you're getting 0. Let's say I have x1 divided by x4. This is 1 over x cubed. Plugging in infinity, you're getting 0. Plugging in negative infinity, you're also getting 0. So these are the only 3 conditions. I do suggest you memorize them. And yeah, that is pretty much it. We can move on to the next page. Use arrow notation to describe the end behavior and local behavior of the function graph in figure 6. Well, with local behavior, they just simply want you to write down the asymptotes and write down as x approaches negative and positive infinity. You can think about this. I'm just going to drink water really quick. Okay, I'm back. So as x approaches negative infinity, what happens? We simply get f of x as x approaches negative infinity. What is it equal to? It equals to 4. So what is the y value as x approaches negative infinity? As x tends to negative infinity, what's the y value? The y value equals to 4. Now, as x approaches infinity, what is f of x equal to? Which means y. I told you this at the very beginning of this year, that f of x equals to y. So we have this, which equals to 4. Now, as x approaches 2 from the left side, why did I write down 2 power negative 2? Okay, f of x. What is f of x equal to? What is the y value? The y value tends to negative infinity. Now, as x approaches 2 from the right side, where is f of x at? It's at infinity. And that is it. It's that simple. Okay. Okay, sketch a graph of the reciprocal function shifted 2 units to the left and up 3 units. Identify the horizontal and vertical asymptotes of the graph, if any. Now, the reciprocal function is 1 divided by x. If you want to memorize this, go ahead. So 1 divided by x is the reciprocal function, or that's what the intentions are of question number 2, example number 2. Now, shifted 2 units to the left. How do I shift? Okay, so let me first write this as f of x, so you don't get lost. F of x equals 1 divided by x. Okay, let me just pull this out. Okay. Remember this. If I want to shift to the left, you're going to have to use this later on. So if you don't write this down, you're just going to have to see it later. So I do suggest you take notes as well, even if it doesn't have to do anything with rational functions. So shift to the left means we're adding to the x value. So let me give you an example. Let's say shift to the left, let's say 3 units. If I have f of x, what does this turn into? If I shift it to the left 3 units, it turns into f of x plus 3. It's that simple. Now shift to the right 3 units as well, what happens? F of x turns into f of x minus 3. Now, what if I want to shift upwards? Let's say 3 units as well. What happens? We add to f of x 3. We don't add to x, we add to f of x. Now, what if I want to shift downwards? Well, this one is pretty straightforward. 3 units. What happens? You subtract 3 from f of x. Now let's apply what we've learned to the reciprocal function. We have f of x, which equals to 1 divided by x. We're shifting it 2 units to the left, so now I have f of x plus 2, which is simply 1 divided by x plus 2. And I'm also, and up 3 units, so I'm adding 3 units. Now I have f of x plus 2 plus 3. Remember, you add to f of x 3, which is simply 1 over x plus 2 plus 3. You then do the math. You don't really need to do the math, actually. Just, what are the, let's write it down here. 1 divided by x plus 2 plus 3. What are the horizontal and vertical asymptotes? Well, remember, vertical asymptotes, you just take the denominator. So we have x plus 2 equal to 0, x equals to negative 2. This is your vertical asymptote. What is the horizontal asymptote? You take the leading term. We don't have any leading terms in this case with the numerator. You can just take 1 and you divide it by x. If this approaches negative infinity, we're going to get 0, positive infinity, 0. So it's the y value equals to 0. This is your horizontal asymptote. I'm going to call it h. This is your vertical asymptote, which is simply v. And it's that simple. Okay? Let's move on to the next question. One second. Okay. A rational function is a function that can be written as the quotient of 2 polynomial functions, p of x and q of x. We're simply dividing 2 functions. Now they're mentioning it. They should have mentioned this at the very beginning. The rational function is just dividing 2 polynomial functions. Now, what else do we have? We have example number 4. Remember domains? Well, we're back at domains now. They're asking us to find the domain of this function. This is very simple. We have x squared minus 9. Well, you can factorize this, or if you want to simply do x squared minus 9 equal to 0, x squared equals to 9, square root both sides. We have x, which could be equal to positive or negative 3. This is one case, or I do suggest you memorize this. A squared minus b squared equals to a minus b, a plus b. If I have x squared minus 9, then this is simply x squared minus 3 squared, which is just x minus 3x plus 3. And you take every single factor, you place it, well, it's not equal to 0, and then x plus 3 not equal to 0, x is not equal to 3, and x is not equal to negative 3. These are the 2 conditions. These are the 2 x-intercepts, actually. X vertical asymptotes, and they're also part of the domain. So let's write down our domain interval notation. We have negative infinity, which is not included, to negative 3, not included, union 3 to infinity, and that is it. Are we good? Now let's move on to example number 5. Find the vertical asymptotes of the following. Well, what am I gonna do? I'm gonna first, Okay, you just take remember, to find a vertical asymptotes, you take the denominator and you place it equal to 0. So I have negative x squared minus x plus 2 equal to 0. I don't want to deal with this negative, so I'm going to multiply both sides by negative. Now I have x squared plus x minus 2 equal to 0. What are the two numbers that I multiply them by each other? They give me negative 2, but if I add them, they give me 1. That would simply be x plus 2 times x minus 1. So x equals to negative 2 is one vertical asymptote, and x equal to 1 is the other vertical asymptote. Now, what else do we have? Okay, we have removable discontinuities, which are basically factors that are present both in the numerators and, in the numerator and the denominator. So in this case, occasionally a graph will contain a hole, which is this point. As you can tell, it's a hole. And a single point where the graph is not defined. Indicated by an open circle, we call such a hole a removable discontinuity. For example, the following function may be rewritten by factoring the numerator and the denominator. We have x squared minus 1, which is simply a minus b, a plus b. And the denominator is pretty straightforward, x plus 1, x minus 3. And as you can tell, x plus 1 is a common factor in the numerator and the denominator. The 0 of this factor is x equal to negative 1. It's the location of the removable discontinuity. Notice also that x minus 3 is not a factor in both the numerator and denominator. The 0 of this factor is x equal to 3, which is simply just a vertical asymptote. So if you have a factor that is present in both numerator and denominator, and that is simply a hole which is tested on the AP, so just memorize it. If you have factor, numerator, denominator, that will simply be a hole, okay? Now, yeah, this just repeats what we just covered. Let me see. Okay, a removable discontinuity occurs in the graph of a rational function at x equal to a if a is a 0 for a factor in the numerator that is common with a factor in the denominator with the numerator. We factor the numerator and the denominator and check for common factors, as we've done. So you can't just tell that just by looking at this, do we have any common factors? No, you need to factor it out first. Once you're done with that, then you can tell if we have any common factors, yes or no. If we find any, we set the common factor equal to 0 and solve. This is the location of the removable discontinuity. Let's say you find this common factor, numerator and denominator. What do? You take x plus 1, you set it equal to 0, x equals negative 1. Well, that is simply your hole, okay? This is true if the multiplicity of this factor is greater than or equal to that in the denominator. If the multiplicity of this factor is greater in the denominator, then there is still an asymptote at that value. Okay, well, what does this tell us? It tells us that if you have the multiplicity of this factor greater in the denominator, then there is still an asymptote at that value. So if I have, let's say, x plus 1 squared, and you have x plus 1 in the numerator, then that still basically means we have x equal to negative 1, as a vertical asymptote. Let's have a look at this one. We have x minus 2 divided by x minus 2, x plus 2. Well, this basically means that we do have x equal to 2, which is a hole, right? And we have x equal to negative 2, which is a vertical asymptote. Do we have anything else? Well, we have horizontal asymptotes, which I did explain on my own. If the degree of the denominator is greater than the degree of the numerator, there's a horizontal asymptote of y equal to 0. So how do I find horizontal asymptotes? Remember, you take the leading term. So let's say 4x is divided by x squared. What does this simplify to? It simplifies to 4 divided by x. As x approaches to negative infinity, what do I get? I get 0. And as x approaches to infinity, what do I get? I also get 0. How do we test this? You go onto your calculator and you do 4 divided by negative 1 billion if you want. You're simply going to get a number very close to 0. And how do we test this one? You do 4 divided by 1 billion, and you're also going to get a number very close to 0. Now, if the degree of the denominator is less than the degree of the numerator by 1, we get a slant asymptote. So let me show you what that means. Let's say we have 3x squared divided by x. This equals to 3x. This is your slant asymptote. It is missing the y-intercept, but we don't really need to solve for that now. And you can do it by simply dividing 3x squared minus 2x plus 1. You do it, remember, like this, x minus 1, and then you just, let's say, yeah, you go with 3x. 3x times 3x is simply 3x squared. Then you got negative 3x. You get plus x plus 1. Then you do plus 1. You get x. Then you get negative 1. We get negative 2, right? Yeah, so 3x plus 1 would simply be, here it is, g of x equals to 3x plus 1 is your slant asymptote. But you're not required to do this now. I don't want you to focus on this. Instead, just focus on that if the degree of the numerator is greater by 1, so let's say 3x4 divided by 3x cubed, this is greater by 1, numerator greater by 1, you're getting x, right? What is the slope? The slope is the coefficient. It's just 1, right? It's 1, which is in front of x. Let's say you get 4x5 divided by 2x4. You're going to be left with 2x, right? What's the slope? The slope equals to 2. And that is the slant asymptote, which is an asymptote that is slanted, which is basically neither vertical nor horizontal. It's oblique, so it looks like this. Okay, anyways, what do we have? Okay, we're done with this. If the degree of the denominator equals to the degree of the numerator, then there's a horizontal asymptote at y. So 3x squared divided by x squared is simply just 3, right? And that is your horizontal asymptote, which is pretty straightforward as well. We only got these 3 examples left and we're done. So if you want to memorize this, go ahead. If you understand it, then that's it. Okay. Now, I do suggest you try and solve this on your own. A, B, and C. Pause the video, assuming you did. So I'm going to solve A. With A, we just divide. How do I find the horizontal asymptote or slant asymptote? I just divide, right? So 6x cubed divided by 2x cubed. I'm left with 3. That is your horizontal asymptote. With option B, I have x squared divided by x. This is greater than the denominator by 1, so I'm going to be left with a slant asymptote, which has a slope of 1. It does have a y-intercept. If you want to find the y-intercept, feel free to divide x squared minus 4x plus 1 by x plus 2. I'm assuming you know how to do this. If you don't, just make sure you message me, I guess. And with option C, how do I solve this? X squared divided by x cubed. I'm just left with 1 divided by x, correct? X squared divided by x cubed is just 1 divided by x. Infinity or negative infinity, you're getting 0. So this equals to 0. That's your horizontal asymptote. Now, what about this? Find the horizontal and vertical asymptotes. Well, if I have, how many x's do I have in the numerator? X squared, right? Denominator, I have x cubed. So 1 divided by x, which is 0. This is my horizontal asymptote. Vertical asymptote, I would take the denominators, making sure I don't have any common factors with the numerators. Do I? No. X minus 1, is it present in the numerator? No. X plus 2, is it present? No. Is x minus 5 present in the numerator? No. Which means all three are vertical asymptotes. X equals to 1, x equals to negative 2, and x equals to 5. You place them all equal to 0. Now, last but not least, example number 10, find the intercepts. You plug in x equal to 0, and then you take the function and place equal to 0. So f of x equals to 0. This is simply the y-intercept. This is y-intercept when x equals to 0. And this would represent the x-intercept when y equals to 0. So let's do the y-intercept first. We have 0 minus 2, 0 plus 3, divided by 0 minus 1, 0 plus 2, 0 minus 5. You do the math, you find the answer. What about the second one? You do x minus 2, x plus 3, divided by x minus 1, x plus 2, x minus 5, which equals to 0. Now if I cross multiply, all of this will cancel out. So I'm just left with x minus 2, x plus 3 equal to 0, right? Now that basically means that x equal to 2 or x equals to negative 3, and these are x-intercepts. And yeah, that is pretty much it for this video. I'm not sure whether we crossed the 30-minute limit, but yeah, that was it. I'm gonna send you 3 other videos regarding rational functions and their problems and all that. And yeah, we'll see you in the next video.